Welcome engineering statics students. This is a mini lecture problem demo on the subject of force resultants for force systems that have distributed loads. And this problem is particularly applicable to any of you all who are going into civil engineering because it demonstrates the typical response of soils to a linear or area load. So the load distribution here is the result of soil pressure acting back on this concrete slab foundation that is itself subject to loads from these columns. So this is literally the way that the soil will push back on a building foundation, and this type of equilibrium analysis excuse me, is the foundation, pun intended, to foundation design for buildings, retaining walls, etc. So this is very, very basic for those of you who are going into that field. It's from our standpoint, it's interesting because in this case, rather than simply analyzing a known distributed load, we're going to find a distributed load from something that's maybe a little easier to calculate in terms of point loads. So it's a reverse of what's typically done in these types of problems. So basically, what we need to know is what's the soil doing, and so we're looking for literally the load per unit length at this point, and the load per unit length at this point in something like, call it, since this is probably civil engineering, we'll go old-fashioned, say, pounds per foot here and pounds per foot over here. That would end up giving us a force resultant somewhere pushing back that is going to have an equivalent force and moment that's going to keep this slab from rotating down into the soil or sinking or flying out of the soil, which is far less likely. It's probably going to rotate. So we want to know what this resultant is to oppose these three loads, which probably isn't too hard, but then we need to know where to put it, and on that basis we want to back calculate what this W1 and W2 are. Why would we need to know that? Because those two values are going to be linked to what the soil's doing. So maybe we got to ask our contractor to go back and do some more compaction so we're getting more force per unit area that the soil can push back with, and that is a function of, say, soil void space and composition. So we'd know what we had to do to get the soil to do what we need. So W1 and W2 are linked to something that we can change on our construction site. So all of that is going to flow from the applied loading. So let's go ahead and set this up. So we can start with just what do we know? We know that the force resultant from the distributed load equals the sum of the forces, and this is all in the vertical. So I could say sum of the forces in the y. Let's go ahead and do that. And as far as that goes, let's go ahead and define a coordinate system. Might be a good time. So let's say that's y and this is x. And from the point of view of this problem, it looks like the slab has minimal thickness. So we can just say that this is the x-axis right here. Okay. So the force resultant coming from the soil has to be the sum of all of the applied forces coming from the column and the resultant moment coming from the distributed load of the soil has to be equal to the sum of the moments from the applied forces. Okay, so let's make ourselves a little FBD of the slab FBD slab to get an idea of what those are. So we've got a point O here, the origin, and we've got 60 kilonewtons at 1 meter. We've got 80 kilonewtons at 1 meter plus 2.5 meters, so that would be 3.5 meters. And then we've got a 50 kilonewton at 6 meters. 2.5 and 3.5 is 5, 6, plus 1 is 7. So the sum of the forces, they're all going down. This is 60 plus 80 is 140, and 50 should be 190. And just to be sure, let's kind of do this twice. So 60, 80 plus, 50 plus. So we have 190 kilonewtons. So we already know now the magnitude of the force resultant under that trapezoidal load. So that's basically that defines the area under that curve. So that's the total area. So now we just need the relative values of W1 and W2, which is going to determine where we put it, basically. So now we need the resultant moment. So that's going to be the sum of the moments. They're all going in the same direction. We can just say they're all going to give us a negative moment. So we're going to end up with negative 1 meter times 60 kilonewtons minus 3.5 meters times 80 kilonewtons minus 7 meters times 50 kilonewtons. So we can calculate a resultant for that, do the math here. So we have 1, it's pretty easy. So negative 60, 3.5, enter, 80 times, plus 7, enter, 50 times, plus, and I'm going to calculate that backwards just to make sure. 7 times 50 should be 350. Enter, 3.5 times, plus, and 60 plus, yep. So we have 690 kilonewton meters. That's the total moment, which means this force resultant, X sub r, is acting at 690 kilonewton meters divided by 190 kilonewtons. So our total moment divided by our force gives us the moment arm, or the R. Our cross product is easy here, everything's perpendicular. So we have 690 kilonewton meters divided by 190 kilonewtons, which gives us something like 3.63 meters. So if we want to simplify our FBD again, we can say the mirror image of that force resultant, or a distributed load, has to equal 7 So if this is 0, we have to go over so our F sub r here is acting at 3.63 meters. So that is going to have to be opposed by, literally, we'll just put this in red. We're going to call it F soil, which is going to have to act at the same effective distance in order to give 0 moment. So what we need to ask ourselves in terms of finding W1 and W2 is, how do we come up with, and we can flip this over to make it a little bit easier, how do we come up with something? And remember, the soil is actually acting on a little bit different area than we considered, because we've got a little bit more room here. So, oh, we have an error. We got a little bit. So let's take a look at where we placed that 50 kilonewtons. Did we put it in the right place? We had 5, let's just make sure, maybe we didn't. 5, 6, 7, okay? Nope, we didn't, we're good. Yay, whew, that's okay. We catch our errors, we fix our errors. It's not the end of the world. But in this case, we were right. So if we have the origin, which is this point, W1, W2, so we've flipped over our soil. This point is at 8 meters, right? So here's our 0 point. We go over 1 meter, 2.5 meters, that's 3.5. 3.5 and 3.5 is 7 to this point, and there's another 1. So the soil is acting over the whole slab, which is actually 8 meters. So we're at 0.0 here. This is all coming down. So if we define a load distribution here, a Q as a function of x, where x is increasing here, we could use our algebra and define a line equation for this. So we could start with a slope and say W2 minus W1 over 8 meters times x plus, when x is 0, the load distribution is W1, so that's plus W1. So let's make sure if we plugged in x equals 8, we should get W2. 8 and 8, W2 minus W1 plus W1 is W2. Okay, so that's our load distribution. And we know that if we integrated our load distribution from 0 to 8 meters, we would get something that when we put in the limits of integration, we should get a value of 190 kilonewtons. Okay. So we can go ahead and do that because W2 and W1 are constants from this standpoint. So let's go ahead and evaluate our integral, or at least set it up what we're going to integrate. We're going to integrate from 0 to 8 meters. W2 minus W1 over 8 meters, all of which is a constant, x plus W1 dx. That's going to be W2 minus W1 over 8 meters times 1/2 x squared plus W1 x evaluated between 0 and 8 meters. Okay, let's make sure we did our integration right. This is all a constant, so it stays. The integral of x is going to be 1/2 x squared. This is a constant. The integral of a constant with respect to x is W1x. Okay, so we can plug in our limits of integration. 0 is going to give 0 for everything. So we basically only have the 8 meters. So we're going to end up with our W2 minus W1 over 8 meters times 1/2 times 8 meters squared, which should be 64 meters squared, plus W1 times 8 meters. We can probably simplify this a little bit, but we'll just take a pause at this point. And remind ourselves that this is all going to have to equal 190 kilonewtons before we get too excited doing all the math. Now at this point, what were we trying to evaluate? W2 and W1, these load distribution values for these 2 points under the slab, because that's going to be linked back to soil properties that we can then dictate when we tell the guy with the compactor to go out there and get our soil bearing capacity, what it needs to be. So I have one equation and I have two unknowns. Well, that isn't any good. Well, it's better than nothing. But it would be really nice if we had another equation. Well, we can write an expression for moment, and just so happens we have a value for moment up here. So maybe we could use our same distribution of load and moment expression for an equivalent moment, which we know the value it has to be that contains W2 and W1. So let's go ahead and do that. We know that the resultant moment, 690 kilonewton meters, is going to have to be the integral from 0 to 8 meters of qx times x. So this time we're going to integrate W2 minus W1 over 8 meters times x squared plus W1x dx. So this is basically the integral over the entire width of this slab, this width, of x q of x. So here was q of x in the integral, here's q of x. Now I've just multiplied that by x. So instead of x, I have x squared. Instead of W1, I have W1x. So I evaluate that integral. and I got the same constant out here, W2 minus W1 over 8 meters. And this time I'm going to integrate x squared, and I'm going to get 1/3 x to the third minus W1 times 1/2 x squared, which is the integral of x with respect to x. And that's all going to be evaluated between my limits of x equals 0 at one end of the slab and 8 meters at the other end of the slab. And that all has to equal 690 kilonewton meters. And the nice thing is we went from kilonewtons to kilonewton meters, and we picked up another length term, which is great. So that would indicate our units are matching. So once again, our lower limit of integration at 0 is going to give us 0 for both terms. So really we just have one number to deal with. So we could write an expression that says W2 minus W1 over 8 meters times 1/3 times 8 meters cubed minus W1 times 1/2 times 8 meters squared equals 690 kilonewton meters. And we now have two unknowns, W2 and W1, and we have 1, 2 equations that we can use to solve them. And I know they look kind of gnarly, and I'm not going to actually crank through them now, but one of the nice things to recognize is that you have a constant term, a constant, this and this is a constant, that's a constant. So really, these are both linear equations in W1 and W2, which are the things you're solving for. So it's a little bit of algebra and simplification, but really not all that hard to solve. Not going to go through it now, but you are definitely poised to where with a little bit of algebra and rearrangement you can get values for W1 and W2 and then go ahead and back check them. You do know about where your force resultant should be, and you can get an idea of if it makes sense and give yourself a level of error checking to do that. So that is an example of basically using our sum of the moments equal moment of the sum, force resultant being the sum of all the incremental forces of a distributed load, kind of being worked backwards to figure out what the distributed load profile would have to be, the shape or the parameters of a known shape of a distributed load to push back on point loads coming from something that we know. So that is it for this mini lecture example.